Now let's look at the describing function of the dead zone nonlinearity. The graph of the dead zone nonlinearity is this. This is the graph of the dead zone nonlinearity. And to construct the describing function, we need to get the output of this nonlinearity for a sinusoidal input, such as similar to the one we have done for saturation. A sinusoidal input is presented to the nonlinearity. Here a saturation is shown, but we'll be doing this for dead zone. And the output is then graphed, which leads us to the piecewise definition of the output, and then the application of the definition of the describing function for the output of the nonlinearity. So this is the input sinusoid, and this is the output of the dead zone nonlinearity. So the graphical procedure is done, and we have computed the output waveform. This procedure is done for the dead zone nonlinearity, and the output is constructed. Output is constructed. It looks like this. So from this graph, we get the piecewise definition, which is this here, and then we apply the definition of the describing function, and it turns out that the B1 coefficient is this quantity by using the limits of the integration in the piecewise definition of output waveform. So the describing function is applying the definition. We have this function is the describing function. It's a real function because there is no phase shift in the output waveform as compared with the input sinusoid. Therefore, this describing function is a real valued function. If we plot this, it looks like this. So this is the dead zone where the describing function is also 0. Likewise, if we look at the backlash nonlinearity, backlash is caused by gears, like we previously described. Backlash is caused here when there is no action because of a little fault in the gear teeth. The driving teeth and driven teeth are incorrectly engaged for that small angle where there is a fault in the teeth, a deformation in the teeth due to overuse or some other reason. So this causes hysteresis type of nonlinearity to manifest. So we need to study this nonlinearity now. So input sinusoid is taken. This is the input sinusoid. This is our backlash nonlinearity, which is a hysteresis. And this is the output waveform for the sinusoidal input. Note that unlike the previous two examples of saturation and dead zone nonlinearities, the backlash nonlinearity is having a phase shift as compared with the input. That's because the forward segment, when the dynamics, when sign is increasing, the lower part of the hysteresis nonlinearity is active. That segment is active. The reverse segment is inactive. When the sinusoid is going down, that is when the dynamics is from right to left, the upper segment of the hysteresis nonlinearity is active, the lower part is inactive. It's because of this reason that the output waveform will have a phase shift as compared with the input. Now we get the piecewise definition from the output waveform, and then we apply the definition of the describing function. It turns out that this describing function is a complex valued function because unlike previous nonlinearities, the function WT here is neither even nor odd. So both A1 and B1 are non-zero. So consequently, this describing function is having a phase shift. This is the magnitude of the describing function as a function of B by A. This is the phase of the describing function in degrees. It is shown here for this backlash nonlinearity, which is a hysteresis. Now the closed loop linear system's characteristic equation is GH equal to -1. So let's look at the nyquist criterion, which could be applied for stability for the nonlinear systems as well. So based upon this equation, Nyquist criterion can be derived straightforwardly by applying the Cauchy's theorem in complex analysis. The criterion can be summarized in the following procedure. Draw in the p-plane the so-called Nyquist path enclosing the right half plane. So this is the Nyquist path there in the p-plane. This is the GH plane. Our x-axis here has real part of GH. Y-axis here has imaginary part of GH. So this plane is the GH plane. This is called the Nyquist plane, and this contour is Nyquist contour or Nyquist path. This is happening on the p-plane. So on the p-plane, we draw the Nyquist contour enclosing the right half plane, map this path into the other complex plane through the GH map. Determine n, the number of clockwise encirclements of the plot of GH around the point -1, 0, because that happens to be the right-hand side of our criterion of the characteristic equation. Compute z, the number of zeros of the loop transfer function delta p in the right half plane by this equation, where p is the number of unstable poles of delta p. The value of z is the number of unstable poles of the closed loop system. So this is the Nyquist criterion. So this is the Nyquist path, and this is the Nyquist plane. You have GH plotted for this contour on the p-plane. Now, when a describing function is used, the loop transfer function will be 1 plus kgh. The characteristic equation will be gh equal to -1 by k, unlike the previous characteristic equation where gh was -1. This is happening because of the describing function. So the same arguments as used in the derivation of Nyquist criterion suggest the same procedure for determining the unstable closed loop poles, with the minor difference that the z now represents the number of clockwise encirclements of GH around the point -1 by k and not -1. So this shows the corresponding extended Nyquist plot. So -1 by k is here. Previously, we used to look at the encirclements of -1, but now we see the encirclements of -1 by k. So it's a complex number, and it lies on the plane. It may not be on the axis, because we saw in the backlash nonlinearity, the describing function was complex valued. So its reciprocal will be a point in the complex plane. It's not on the axis. So if a self-sustained oscillation now exists, which is a limit cycle, of amplitude a and frequency omega of the system exists, then the variables in the loop must satisfy these equations. So the governing equation for our case, that is under no input, it's a self-sustained oscillation. So there is no external input, but there is a sustained oscillation. For that condition, the algebraic condition becomes this. This is the mathematical condition for self-sustained oscillation. So from this, if the graphs of gg omega -1 by n of a omega is plotted, we look at the intersection of these two graphs. So that is what is depicted here. The gg omega plot is this, and -1 over n of a plot is here. So the intersection points are the likely candidates of limit cycle. So when the describing function is a function of both a as well as omega, we have multiple points of intersection, each of which is a limit cycle candidate. So we note that these 1 over n plots are plotted here for each value of omega. If the intersection point, at the point of intersection, the omega on the gg omega curve at this point, for instance, is also omega 1, then this intersection is a good limit cycle candidate. If the omega of the gg omega curve is not omega 1 at this intersection point, it's not as good a candidate for limit cycle. So this graph allows us to detect the possible limit cycle occurrences. So now we look at the stability of the limit cycle. Each intersection point of the curve g omega and the curve minus 1 over a corresponds to a limit cycle. If points near the intersection and along the increasing a side of the curve minus 1 by n are not encircled by the curve g omega, then the corresponding limit cycle is stable. Otherwise, the limit cycle is unstable. So let us look at this example, this schematic picture, where you have minus 1 over n plotted here and g omega is here. There are two intersections. So there are two limit cycle candidates in this problem. So we want to know which one of these is stable. So the criterion now says, at the point, this is the increasing a direction for minus 1 by n curve. This is the increasing a direction. So points near the intersection and along the increasing a side of the curve, this is the point of intersection. Let's look at this. This is the increasing a side of the curve. If the increasing a side is not encircled by g omega, then the corresponding limit cycle is stable. Otherwise, the limit cycle is unstable. So if I look at L1 point, so the point near the intersection and along the increasing a side of the curve. So this is the increasing a side of the curve. They are, in this case, at L1 point, they are encircled by g omega. So this is an unstable limit cycle. If a limit cycle exists there, it's an unstable limit cycle. Here, at this point, this is the increasing a direction. It is not enclosed. It's not encircled by g omega curve. So this limit cycle is, if there's a limit cycle there, then it must be a stable limit cycle. The describing function method for detecting the occurrence of limit cycles is an approximate method. There are three kinds of inaccuracies possible. The amplitude and frequency of the predicted limit cycle may not be accurate. Predicted limit cycle may not actually exist. An existing limit cycle may not be predicted. So the describing function method is an extension of the frequency response method of linear control. It can be used to approximately analyze and predict the behavior of important classes of nonlinear systems, including systems with hard nonlinearities. The desirable properties it inherits from the frequency response method, such as graphical nature and the physically intuitive insights it can provide, make it an important tool for